Georg is the director at the University Medical Center of Rostock, and he is also an adjunct professor here at UCD. So he's a leading figure in medical bioinformatics and has a distinguished career dedicated to unraveling the complexities of aging through computational and systems biology approaches. So we're really, really excited and lucky to have Georg here today. So please, let's welcome him and his talk.
Yeah, thank you very much. I'm grateful for the opportunity to talk about longevity interventions and also generative AI. And the overall context of this is, okay, there's lots of adversarial and dangerous applications of AI. And like what Dario Amodei is saying here, we have to focus also on the positive. There must be something we are fighting for, some positive, some outcome of AI. And I think employing AI for longevity, for improving health, is one of the really positive outcomes we can have. So this will be the second part of my talk. In the first, I'm having a few slides on interventional versus observational data, which I think is an important point that is also being overlooked by many people. And yeah, you have got many news now every few months about some, for example, here Nutraceuticals tested as an anti-aging or longevity intervention. And quite frequently, after 1 year, they're then looking at epigenetic age. And we've learned a lot about epigenetic age in the last session, and there's this epigenetic age acceleration that you can calculate based on those methylation plots. And then, for example, if this acceleration is negative, like -2, -5, you can claim that it's providing people with a younger age in some way. So here in this case, 1 year of this botanical, and people were 2 to 5 years maybe younger. But yeah, there are similar claims for alpha-ketoglutarate, for example, which is even supposed to give you 8 years and exercise. But there is a caveat. This epigenetic age acceleration is calculated based on this aging clock that is based on observational data. It's trained on observational data. And then it's used to judge interventional data. And yeah, that's a big problem, I think, because if you now try to think about the setup, so essentially this is a kind of decision surface of a classifier. There's a similarity space, and the classifier was trained that on this side there are lifespan extending interventions, and on this side there are not lifespan extending interventions. And if this is intervention data, all the plus, maybe there's a problem here or there, but there is a bit of noise. But overall, it's a pretty clear-cut decision that is allowed by this classifier that was trained to distinguish the plus from the minus. And if you've got a new intervention, that's a question mark here, and you can say, okay, with some confidence, it's an intervention that does not extend lifespan. However, on this other side, you've got, in the similarity space, observational data used to train the classifier. Like young tissues and cells were used here, old tissues or cells were used here on that side, and then decision surface distinguishing the plus from the minus. But this is observational data. It's usually done for the aging plots. And then if you want to classify an intervention, in a way you are lucky if it goes here at the decision surface, you can't say anything. Because if it goes here in the plus or the minus, the problem is you have got a pretty clear classification, but it may just be wrong because this is observational data, and that is And that here is an intervention to be classified. And observational data are full of confounders. One example, recent one, is actually dietary patterns for healthy aging. And they looked at observational data from the UK Biobank, and they saw some kind of things that made sense, like fruit is good for you, berries and olive oil, but also eating fast and fried foods is really good for your health, based on this huge data set. And they are at a loss of explaining this. There are some confounders, maybe that people who eat fast and fried foods are very social, who knows? But you see, there's a big problem with observational data, and it would be much better to go for interventional data. And this is now coming. This is a preprint from Pedro on mouse data, actually. And there were a few attempts already on worm C. elegans data some years back. But this is actually the first time in mouse data predicting lifespan extending chemical compound effects with intervention data. It was published just a few months ago, end of last year. And this is a table just demonstrating how much interventional data there now is. I collected this one a few months ago. There are also some data focusing on toxicology, but other ones on nutrition interventions and so on. And Mats Unfried, some of you may know Mats Unfried, just 2 months ago he said, okay, there must be a global human intervention testing program. And I think that is the right direction here. So I summarized it in a review which just came out about a month ago. And in this review, I also had the second point. When you're doing the classifier learning, you should be using the best possible methods. Not just that you use intervention omics data as the input, and then in the end you want to have predictors for intervention outcomes, but also that you are using the right feature selection, the right classifier learning, possibly by automated machine learning. And they should be interpretable. So the features and also the entire classifier should be interpretable. If you want to know biologically what's going on, that's the green part here. Whereas here in the blue part with neural networks, interpretability may get lost. And then this was in December last year. I was interested, can AI, now I'm coming to AI, actually design and execute such a pipeline? And at that point, I only got to a little bit of doing those principal component analysis by AI. That was work done by Anton Kulage and Nikolai Uzanov together with me, and there were 2 PCA plots we could generate, or we could ask the AI to generate based on gene expression omnibus data, and it was kind of a lost case. That was last November, December. I wrote a grant application for the German Research Foundation, nevertheless, but with the idea to use AI maybe in the future. That application was actually funded, and then just a few months later, in February, I was actually possible to generate an entire draft of a DFG grant application by AI, which was pretty reasonable. Nothing perfect, but it had all the components, a Gantt chart, and so on. And that was then done with OpenAI Deep Research. First, the topic was longevity. And now, just a few weeks ago, with agents, it's becoming all the more powerful to use AI for such tasks, for classifiers, designing and executing them, and so on. And this is based in part on the model context protocol. This is a way to combine AI systems, connecting AI systems and tools together. And this was introduced by Anthropic. This was actually, Anthropic's a company from Dario Amodei, who I quoted in the very beginning. And Anton is now using, and his colleagues, they are now using the model context protocol to tie together bioinformatics tools. And that was just a week ago, they got $10,000 as an award for their efforts. And this Holy Bio MCP, they call it, by Anton, Livia, and Nikolai. This is essentially a federation of specialized MCP servers. And you've got an interface then to core bioinformatics tasks like BLAST or also classifier learn or enrichment analysis, to the bioinformatics databases. Also specifically for longevity, there's a database called OpenGenes. And also there's actually even a synergy database specifically for genetic interactions for longevity. And this is now how it can be done. It's really an almost magical thing. We can ask in natural language the system based on the MCP, get the lifespan extension and synergy data for the following genes from C. elegans, and the list of genes, and place them into a file. And you can select the sets of tools that are then used by the orchestrating language model, and that model then it responds, it gathers information about, as we want, genetic synergy and aging on the databases. It retrieves a database scheme. And then it actually executes SQL database queries based on that scheme, all automatically. And then it goes to synergy age. It finds, for example, for this DAF2 and for SOT1 that they may be acting synergistically, and then you can go even further. You can look at another gene here, SOT1, which is also implied in that synergy. You can take a look at how conserved it is. You can get alignments automatically generated comparing the sequence in human with the one in worm, telling you something. You can do drug discovery stuff, molecular modeling. This is not coming in the last weeks and months. That this is now possible with AI. Okay, and now in the last part, it's a related task we just completed a few months ago. It's a preprint available where we have the question of benchmarking large language models for personal health recommendations. And what we did here, we gathered 6 experts who developed 25 cases, also with model answers. That is, here it means answers that should be returned by a large language model. To questions like, should I take supplement X? I'm 55 years old. This kind of questions. And we asked overall 6 language models in a variety of ways. We got almost 50,000 answers to analyze. And this can no longer be done manually. So we did a large language model as a judge. And then we asked it, is the response correct? Is it comprehensive? Is it complete? And so on. And the bottom line after some statistics is actually the commercial models gave better recommendations. So whenever possible, you probably want to pay for it. And also, when you refer to the assessment criteria, like you tell the model when you are asking it, I want to have an answer that is correct, that is comprehensible, and so on and so on, then you indeed get slightly better recommendations. It's significant, it's not so much, and I guess as models improve, this advantage may even be going away. Okay, and then regarding benchmarking AI, I just want to spend half a minute on an application we recently submitted. There are 4 groups, and we want to kill 4 birds with 1 stone. Namely, we want to develop a generative AI agent that can predict drug combinations with synergistic effects based on warm data. We want to develop a secret data set of synergistic drug combinations that way, because you can automate it with a worm. The worm gives you data very fast. And this is a secret data set the AI cannot cheat. If you're then asking it to learn a classifier, you can test it with that seated data set, and it cannot find the data anywhere on the internet. So it's pretty good way. You want to discover synergistic drug combination, extend the lifespan of worms, maybe in human. And we also want to have molecular mechanistic understanding of synergistic effects. And I believe in a way that's a goal in the future. There's a lot of value in data sets that are kept secret and that are not accessible to AI in any way, because that's how we can assess it in an unbiased manner. Okay, and the other one, also already agree, you may know about the robust mouse rejuvenation. Atze Kowal from my team especially also contributed there with some modeling, simulation, and AI. And finally, I'm now actually in the process of generating an entire doctoral thesis. In biodata analytics, I can now get a very nice introductory chapter, and I can already have the AI doing analysis that it proposes and that it executes. And the big problem then is finding out whether those analyses are really executed or whether that is just hallucinated. That's a big problem now, but otherwise I kind of have a graduate student kind of at my disposal, and like it for a graduate student, I do not know whether that was done correctly or not. And so benchmarking is really a very important topic here. And finally, I think across the entire scientific value chain, it's more and more easy and possible to use AI to optimize and generate ideas, to generate experimental protocols, data analysis plans, data analytics, get it executed, to generate the publications, at least to generate drafts that are then checked by humans. And then you have to, you can use this model context protocol in other better ways and those deep research tools. But of course, if you have collaboration partners, you need to ask for permission if you want to use their data. That's it. Thanks so much. Yeah. Here's the questions.
We might have time for one question. Just make sure you say it loud so the cameras can pick it up. Didier?
Yeah, thank you, George. It's really very, very interesting. I hope I will have the video soon to see it.
Yeah, there's a YouTube video of this.
Okay, but I have
MCP.
one comment and one question. My comment is, please don't use statistics or information about healthy lifespan because they are not reliable. Because I saw you, okay. That's also for a discussion. But, and my question is, you used only one time the term hallucination, and as far as I know, this is the problem number one with LLMs, and you speak about crossing tools. What is for you at the moment the best way to detect hallucinations, and using which tools that you should cross? Or
Yeah, in the end.
Say maybe in the best world situation, it would be okay. For example, with ChatGPT plus Claude, you can find hallucination of the one.
Yeah, you must check the AI output. Even in those newest tools, there are still those problems, and the best way to check is human work. So you can also use AI to check AI, but that's a bit problematic. But on the other hand, I think hallucinations, imagine there are no longer any hallucinations, almost no hallucinations. I think that's far more dangerous in the end, because then people start using AI output without ever checking. I hope that in a way it will always be checked, the AI output, because you can never be sure. It could also be manipulated. And yeah, you have to be careful there, that's true.
Thank you, George.